Once again, welcome back everyone. Today we've reached the 7th episode of the Computer Vision Systems course. Just like in the last episode, today we'll continue talking about lenses and optics. While in the previous episode we focused on the geometric optical system to understand how lenses work, today we'll start talking about real lenses and look at some parameters. In the last episode, we saw how lenses are able to bend light rays, and to do this, we assumed the use of thin lenses. However, as we know, lenses are not thin. In fact, they usually have a thickness that can sometimes be quite significant. Additionally, lenses have two mechanical adjustments, two rings, which on one hand allow you to adjust the focal length of the lens itself. And on the other hand, they regulate the amount of light that can pass through the optical system and the lens, and thus reach the sensor. Let's now understand what these two adjustments are actually for. Let's start with the focus adjustment. As we've already defined, the focal length of a lens indicates the point where light rays converge when they originate from a point located on the plane, an object that's very far from the lens itself. And what's the difference between two lenses with a 20? Different focal lengths? The focal length primarily determines the scene viewed by the camera. Specifically, the greater the focal length, the smaller the scene captured will be. This effect is very clear in the image you see here. If I use a very short focal length, for example 16 millimeters, the scene captured by the camera is very wide. But as the focal length increases, the scene gets narrower and narrower, and I can see details that I couldn't see before. The second adjustment is related to the lens aperture, or iris, to draw a parallel with the human eye. By adjusting the lens aperture, you can mechanically control the amount of light that actually enters the lens. And therefore, this light hits the sensor of the camera on which it is mounted. The lens aperture is usually indicated by a parameter called the f-number. The f-number, by definition, is the ratio between the focal length and the diameter of the lens itself. This means that as the diameter increases, the f-number decreases. This is possible thanks to a mechanical movement of the iris, which, by opening and closing, allows more or less light to pass through the lens itself. But now let's try to understand what the f-number really is, what it's for, and what values it can take. If I want the light to pass through a smaller area, exactly 1/2 of a, the diameter of the lens must decrease by a factor equal to the square root of 2. This is a consequence of the formula for calculating the area of a circle. And if we calculate the f-number in this condition, it will be equal to 1.4, which is exactly the square root of 2. If we wanted to have the area of the circle through which the light passes again, we would have to decrease the diameter once more by a factor equal to the square root of 2. And so the f-number will be equal to the square root of 2 times the square root of 2, which is 2. Having the area again, the diameter will decrease once more by the square root of 2, and the f-number will become 2.8, and so on. For this reason, the f-number always takes on values like 1, 1.4, 2, 2.8, etc. Each value corresponds to an aperture of the iris such that the area through which light passes is halved compared to the previous value. And what aperture and f-number control? Since they are related to the amount of light entering the lens, aperture and f-number control the brightness of the final image captured by the camera, just like the sensor's exposure time does. Specifically, a low aperture and a high f-number produce a darker image. A high aperture and a low f-number, on the other hand, produce a brighter image. The brightness of an image can be adjusted through two factors, either the sensor's exposure time of the camera or the lens aperture. Now let's define another parameter related to lenses, depth of field. Depth of field refers to the distance between the nearest and farthest planes that are in focus with the lens. We will see that this is related both to the focal length of the lens and to the f-number, and therefore to its aperture. To better understand depth of field, however, we first need to understand what it means to focus an image. That is, when an image is perfectly in focus. In the image you see here, for example, which might appear to be perfectly in focus, if we zoom in on a detail, we can see that the focus might not actually be optimal. And this isn't just related to the resolution of the image, but it's actually due to the fact that, sometimes, focus isn't completely objective. Now we need to consider some effects that occur when a light ray is bent. If we take, for example, a point on the plane, an object that's perfectly in focus, the light rays coming from this point are bent by the lens. For this reason, light rays undergo a certain amount of diffraction and are also affected by passing through the lenses themselves. This means that the point, which is perfectly in focus on the object plane, appears on the image plane with a certain blur, which we call the circle of confusion. Because of these effects, I will always have a point that's slightly out of focus. Since these effects are very small, I will always perceive a point as being in focus, even if it actually isn't. To understand the concept of depth of field, we therefore need to take this effect into account. And to do that, let's go back to talking about geometric optical system. In fact, we know that a point in the object plane focuses at a specific distance from the lens on the image plane. Actually, if we take into account the blur we've talked about, we can also consider as being in focus those points that are a little before and a little after the area where the light rays intersect. This is precisely because we shouldn't think of the point as being perfectly in focus, but rather we need to consider its circle of confusion. This means that I will have more than one plane of focus, and therefore I will have a certain depth of field. But now let's see how depth of field is related to the distance of the point in the object plane and to the diameter of the lens. Let's start by considering a point P. P, in the object plane, it is placed at a distance so from the lens. This point is focused at a distance SI in the image plane. Now let's take a second point P1 in the object plane at a distance SO1 from the lens. The light rays coming from P1 intersect at a distance from the lens, called SI1, in the image plane, which is less than SI. However, because I can also consider a point to be in focus as long as it has a certain circle of confusion, we can consider point P1 to be in focus in the image plane, even at the distance SI. This means that at that distance, both point P and point P1, which is farther than P from the lens, are focused. Now let's add a third point, P2, placed in the object plane at a distance SO2, which is less than SO. Geometric optical system theory says that point P2 will focus in the image plane at a distance SI2, which is greater than SI. But again, since I can consider a circle of confusion of a certain diameter as being in focus, I can say that point P2 also focuses at a distance SI. To sum up, considering the circle of confusion, P, P1, and P2 all focus at a distance equal to SI. This means that in the object plane, there isn't a single point that focuses at a distance SI. But there is a range of distances, the depth of field, in fact, such that any point within this range will always focus at a distance SI. The depth of field depends on the distance of the object from the lens. Specifically, objects placed very far away will have a very large depth of field. The closer the object gets, the more the depth of field will decrease. This is why, when I look at the mountains, which are generally at different distances from me, I see everything in focus. But if I look at my finger and focus on it, I'll see the background completely blurred. And what happens to the depth of field? What happens when I change the aperture, that is, the diameter of the lens? Let's go back to the same diagram. Point P at a distance SO that focuses on the image plane at a distance SI. A second point, P1, at a distance SO1, which focuses at a certain distance on the image plane SI1. And finally, a third point, P2, at a distance SO2 from the lens, which focuses at a distance SI2 on the image plane. This time, let's try decreasing the diameter of the lens. In this case, as you can see, the rays will be more parallel to each other. This means that the same circle of confusion as before forms much earlier than SI1, and much later than SI2, effectively increasing the depth of field. This means that the smaller the diameter of the lens, and therefore the larger the f number, the greater the depth of field of the image will be. These are the most important parameters related to lenses. We have seen how they affect the final image in relation to the size of the scene, the brightness of the image, and the depth of field. Now we are ready to develop a real vision system.